Good morning, students. It's Monday, August 17th, and this is Mr. Lawson kicking off the week with an introduction into your course and kind of digging into our content for the very first time to get us started on the nitty-gritty parts of this of your physics or IPC course. I hope you have a good weekend. This video might go a little long, so just bear with me, and we'll get through it. So, as you know, physics and IPC are science courses. Okay, you've had science courses in the past. In your younger grades, some of y'all might have had chemistry. Others might just be coming out of 8th grade and moving into high school courses like IPC. But many of us don't really understand what science is and its importance. And that by learning physics and learning IPC and validating some of the things we're going to talk about, we'll be doing science. So what is science? If you haven't already, go back to your Google Classroom page and do your warm-up that asks the question, what is science? Okay, if you haven't done already, pause this video, go into your warm-up, and then come back here. Okay, because that's what we're going to talk about next. So what is science? Science is the knowledge about or study of the natural world based on facts learned through experiments and observation. Okay, the word science probably brings about many different pictures, right? Textbooks, white lab coats, microscopes, an astronomer peering through a telescope, right? Einstein's equations on a chalkboard, space shuttles, bubbling beakers, right? All those images reflect some of the aspect of science, but none of them provide the full picture because science has so many faces, right? Oh, I ain't ready for that yet. Science is both a body of knowledge and a process, right? It's exciting. Science is useful. Science is ongoing. And it's a global human endeavor. Let's watch this video by Neil Tyson. He's an astrophysicist, an astronomer, and he provides some interesting insights on the importance of science in America. Okay, why is it important that you guys, just teenagers, understand science and know what it is? Why is it important, and why is it that as a society we must understand science and its definition and its purpose? Think about that as you watch this video. Okay, I want to play it and hopefully you can see it. Okay, we'll see what it looks like. There we go.
How did America rise up from a backwoods country to be one of the greatest nations the world has ever known? We pioneered industries. And all of this requires the greatest innovations in science and technology in the world. And so science is a fundamental part of the country that we are. But in this, the 21st century, when it comes time to make decisions about science, it seems to me people have lost the ability to judge what is true and what is not, what is reliable and what is not reliable. What should you believe, what should you not believe? And when you have people who don't know much about science, standing in denial of it and rising to power, that is a recipe for the complete dismantling of our informed democracy.
Let us demand that educators around America teach evolution not as fact, but as theory. Increasing number of parents showing skepticism about vaccinations. Voters have approved a ban on GMOs.
Call climate change unproven science.
That's not the country I remember growing up in. Not that we didn't have challenges. I'm old enough to remember the 60s and the 70s. We had a hot war and a cold war, the civil rights movement, and all this was going on. But I don't remember any time where people were standing in denial of what science was. One of the great things about science is that it is an entire exercise in finding what is true. The hypothesis, you test it, I get a result. A rival of mine double checks it because they think I might be wrong. They perform an even better experiment than I did, and they find out, hey, this experiment matches. Oh my gosh, we're onto something here. And out of this rises a new emergent truth. It does it better than anything else we have ever come up with as human beings. This is science. It's not something to toy with. It's not something to say, I choose not to believe equals MC squared. You don't have that option. When you have an established scientific emergent truth, it is true whether or not you believe in it. And the sooner you understand that, the faster we can get on with the political conversations about how to solve the problems that face us. So once you understand that humans are warming the planet, you can then have a political conversation about that. You can say, well, are there carbon credits? Do we do this? Do we put a tariff on this? Do we fund? Do we subsidize? Those have political answers. And every minute one is in denial, you are delaying the political solution that should have been established years ago. As a voter, as a citizen, scientific issues will come before you. And isn't it worth it to say, all right, let me at least become scientifically literate so that I can think about these issues and act intelligently upon them. Recognize what science is and allow it to be what it can and should be in the service of civilization. And it's in our hands.
So what do you think? What are your thoughts on what he had to say? What did you get from that video? Think about that as we continue, and as you do your assignment after this video, and really ponder on what the importance of science is, and why it's important that you guys know how to do science. All right, we're not just learning physics or chemistry or biology. That's not why we're here. That's not why I'm here. Yeah, we're going to learn those things. Right, especially in my class, we're going to learn physics. My IPC guys, we're going to learn chemistry. But really, my job is to teach you how to become scientists. Right, how to perform science, so that when you leave this class and go to the real world, or you go to college, you start doing research, or just making informed decisions, even if you're not in a STEM field, that you do it effectively. And that is for the betterment of people around you as well as yourself. Okay, so a little background. We're looking more into what science is. Like I said, it's not just lab coats, microscopes, Science is both a body of knowledge and a process. Right? In school, science may sometimes seem like a collection of isolated and static facts listed in a textbook, but that's only a small part of the story. Just as importantly, science is also a process of discovery that allows us to link isolated facts into coherent and cohesive understandings of the natural world. Science is supposed to be exciting, right? We're supposed to have fun doing it. Science is a way of discovering what's in the universe, how those things work today, how they worked in the past, and how they're likely to work in the future. Scientists are motivated by the thrill of seeing or figuring out something that no one has before. Right? In our course, we're not likely going to do discoveries, but we can follow up on someone else's discovery. Right? We're not going to make some huge finding, but we're going to have fun validating them. Science is useful. The knowledge generated by science is powerful and reliable. It can be used to develop new technologies, treat diseases, and deal with many other sorts of problems. Science is also ongoing. Science is continually refining and expanding our knowledge of the universe. As it does, it leads to new questions for future investigation. And science will never be finished. We'll never reach a point in humanity where we say, okay, we've learned it all. We just won't. So that means it's ongoing. Science is also a global human endeavor. People all over the world participate in the process of science, and you can too, and you're going to. And you may even do it already, and you don't know it. You ought to be doing science. Just making simple decisions in everyday life. Okay. So basically, to get a grasp on what science is, we'll look at a checklist that summarizes key characteristics of science. Okay, the University of California at Berkeley described it really well and gave science 7 key characteristics. The first one, it focuses on the natural world. Science asks questions about the natural world. This includes the components of the physical universe around us, like atoms, plants, ecosystems, people, societies, and galaxies, as well as the natural forces that work on these things. Right? The natural world includes components of physical universe. In contrast, science cannot study supernatural forces and explanations. It's outside of the bounds of science. A lot of supernatural things. For example, ghosts or religious spirits. And while we can do science to support these ideas, it's outside the realms of science to confirm them. Right. So we're talking really about the natural world. So there's all kinds of questions, like what is the natural world, right? Like when did the oldest rocks form on Earth? That's one of the questions of the natural world that we use science to affirm. What chemical reactions do fungi get energy from nutrients they absorb, right? What causes Jupiter's red spot? How does smog move through the atmosphere? Very important questions. Okay, next on the checklist, it aims to explain the natural world, right? Not just focuses, but aims to explain it. The knowledge that is built by science is always open to question and revision. Okay, remember that. All right. Despite the fact they are subject to change, scientific ideas are reliable. The ideas that have gained scientific acceptance have done so because they are supported by many lines of evidence, right? And that evidence, as we said, aims to explain the natural world. Science uses testable ideas. And only testable ideas are within the purview of science. For an idea to be testable, it must logically generate specific expectations. Okay? So for us to do science on an idea, right, it's not good enough to speculate. It has to be testable. There has to be some way we can validate it. For example, consider the idea of a sparrow song. Okay? A sparrow song. So for those who don't know, a sparrow is a songbird. Okay? And the question is it genetically encoded? Or is it affected by the environment in which it's raised? Okay? Let me show you. I'm going to go to this next page. We'll go back in a second. Right? The question is a sparrow song genetically encoded or learned? See what happens when a sparrow is raised in the nest of another species, right? That's the question. Can we test it? Well, yeah, we can, right? For example, if we get a sparrow and raise it with crows, what will happen? One of two things. The sparrow will grow up to sing the usual sparrow song. If it's raised with crows and it sings the same song, it's genetically encoded. But what if it's raised by crows and it starts calling? Right? You've never seen a sparrow call, but had it been raised by crows, would it have? If it does, that means the song is learned. Okay, that's a testable idea. Right? It goes beyond just speculation. If an explanation is equally compatible with all possible observations, then it is not testable and hence not within the reach of science. Okay? So an idea must be testable. Next, science relies on evidence. Ultimately, scientific ideas must not only be testable, but must actually be tested. Okay? It's not enough to be testable, it has to be tested. Preferably with many different lines of evidence by many different people. Okay? Many different people often refers to peer review. You can research that if you'd like, what that term is, what peer review is. Very important in the research field. But this characteristic is the heart of all science, okay? It's the heart of all science. It must have evidence. Even if the test is difficult, it means, for example, spending years working on a single experiment. Right? Scientists actively seek evidence to test their ideas, even if it's difficult. I know when I was doing research, I walked many miles out in the desert alone with nothing but a backpack and a field notebook. Right? It was hard, making some of the discoveries I did. I wouldn't say they're discoveries, but some of the field research. Okay, and that goes with all science. It may be hard, but it's necessary to have that evidence, to have that data for affirmation. In science, ideas that are not supported ideas are protected from testing, that are protected from testing are only allowed to be tested by one group with a vested interest in the outcome and are not a part of good science, right? If there's an idea that can only be tested by one group and not affirmed, across the board, that's interdisciplinary or can be peer reviewed, that's not good science. Okay. Next, like we kind of touched on before, it involves the scientific community. The progress of science depends on interaction with the scientific community. That is, the community of people and organizations that generate specific ideas, test those ideas, publish scientific journals, organize conferences, train scientists, distribute and research funds, etc. Right? Science cannot move forward without these things. All right. It's very key. It's important. In addition, much scientific research is collaborative, with different people bringing their specialized knowledge to bear on different aspects of the problem. Right? Because not only, does it just or let me step back. When we talk about the community of people and organizations that generates scientific ideas, right? It's not. It's one thing to test an idea and affirm it yourself, where you gain evidence and you look at it and you say, okay, this is what I've found. This is what I've discovered, right? Have someone else test it. Challenge you. Like I said in the video on Science in America, right? He said that those ideas must be challenged by his rivals. And that's an important idea because what if you're wrong? Right? What if you missed something? That's the importance of the scientific community right here. Scientific community. That's the importance of that. Next, it leads to ongoing research. Right? Science is an ongoing endeavor. Right? We said that earlier. It doesn't just stop. Most typically in science, answering one question inspires deeper and more detailed questions for further research. I don't know if you've ever heard this quote, but I learned it in one of my fifth grade science classes. Right? Standing on the shoulder of giants. I can't tell you who said it, but in science, many of the discoveries is because those scientists are standing on the shoulders of giants. What does that mean? That means that somebody before them laid the foundation, the groundwork for what they've discovered, and so on and so forth. As more discoveries are made, it's often built on what someone else has done, right? And we know more and more each time. So it's an ongoing endeavor. And finally, science benefits from scientific behavior. And participants in science behave scientifically. And this is what I expect you to do, right? As one of my students in a science course. Science is sometimes misconstrued as an elite endeavor in which one has to be a member of the club in order to be taken seriously, right? Well, and when you talk about the research field of science, in the universities and stuff, if you're not published or you're not an important scientist that's often in scientific journals, a lot of people don't take you seriously. But that simply should not be the case, right? Anybody can do science, and you can behave scientifically, even if you're not a member of the club, right? That's the same thing here. Guys, just because you're high school students, and just because you're not at a university doing research, does not mean we cannot behave scientifically. We can come in this classroom every day expecting to learn something new, something we can validate ourselves by taking control of our learning and being scientists. Science is now open to anyone, right? If you read in the history books, just not that long ago, a couple hundred years ago, not all science was accepted, right? And the in the Middle Ages and even into the Renaissance period, scientists were often ridiculed by the Catholic Church and other religious organizations, right? They didn't accept it. If science went against someone's worldview, then it was deemed as blasphemous or simply not true. Right? Just because science challenges your worldview doesn't mean that it's not to be taken seriously, right? And not anyone could do it back in the day, but nowadays we can. Women, minorities, anyone. But what exactly does one have to do to behave scientifically? There's a scientific code of conduct I want to go over with you real briefly that describes that. Right? How do you behave scientifically? Well, here's the code of conduct. Pay attention to what other people have already done. Right? Scientific knowledge is built cumulatively. If you want to discover exciting new things, you need to know what people have already discovered before you. This means that scientists study their fields extensively to understand the current state of knowledge. You must expose your ideas to testing. Right? You must assimilate evidence, right, by testing whatever your idea is. You must openly communicate ideas and tests to others. Communication is important for many reasons, guys. If a scientist keeps knowledge to her or himself, others cannot build upon these ideas. Right? Remember what we said earlier, science is a community, right? Or someone to double check your work or devise new ways to test the ideas. Next rule, play fair, act with scientific integrity. Hiding evidence, selectively reporting evidence, faking data directly thwart science's main goal, to construct accurate knowledge about the natural world. Hence, maintaining high standards of honesty, integrity, and objectivity is critical to science. A lot of this might be going over some of your guys' heads, right? You're like, Mr. Lawson, this is a high school course, you know. We're not going out and doing research, making groundbreaking discoveries. I know that, but who's to say that some of y'all that are sitting in this that's sitting in this physics or IPC course isn't going to one day, right? That's not my job to determine. That's up to you. But it is my job to make sure y'all know how to perform scientifically. Okay? So if you're questioning, okay, why are we going to know this? This isn't physics, it's IPC. Yeah, but it's the groundwork. Right? These are the rules and the thinking that the pioneers of these subjects had, right? And these rules are something that you can take with you every day. Anytime you do something scientifically, working in the shop, working with your hands, your tools, doing carpentry, welding something together, trying to make something work through trial and error and experimentation, right? It's not just physics, chemistry, biology. It's much more than that. But like anything, science has limits, right? There's some things that science just simply cannot do. Science cannot make moral judgment, right? Cannot make moral judgment. What does that mean? Like, for example, when is euthanasia the right thing to do? Right? We know science shows what euthanasia does. Like, let's say you have, God forbid, a sick animal. Right? Your horse gets hurt and can't perform anymore. When is it moral to do that? Well, science can't tell you that. Right? That depends on your morality, your ethics, and your worldview. What universal rights do humans have? Science cannot determine that. Next, science does not make aesthetic judgments. Science can reveal the frequency of a G-flat chord, right? Like if you're playing music, because music is aesthetically pleasing, or how our eyes relay information about color to our brains, such as in a painting. But science cannot tell us whether a Beethoven symphony or kabuki performance or Jackson Pollock painting is beautiful or dreadful. Right? It cannot. So it cannot make aesthetic judgments. Science doesn't tell you how to use scientific knowledge. Right? That's an important one. Despite what you may see on the news or what you see or what your grandparents may tell you, America's more educated now than they ever have been. People just know more now because there's more information. We've learned a lot more just in this last century than many centuries before. And as you know, because we're not all, but mostly educated, we mostly have some idea of some scientific knowledge. We don't always interpret them the same, right? For example, a debate on climate change. We all have the data. We all have the facts. But it's not science's job to determine what we want to do with that data. Next, science does not draw conclusions about supernatural explanations. Do gods exist? Do supernatural entities intervene in human affairs? Is the person that's doing palm readings or reading through a crystal ball really seeing that? Who are they talking to in there? It cannot draw conclusions about supernatural explanations. It can get evidence to support these things. I do believe that, but it cannot draw conclusions, right? Because it's beyond the realm of nature. And what do we say science is? Right. It studies the natural world. All right. Moral judgments, aesthetic judgments, decisions about applications of science, and conclusions about the supernatural outside the realm of science, right? So that means it's a limitation. But that doesn't mean that these realms are unimportant, right? These are all important. All four of these. In fact, domains such as ethics, aesthetics, and religion fundamentally influence human societies and how those societies interact with science. Right? All these things influence what we do with it, what we do with science. Right? And neither are such domains unscholarly. Right? Just because you have a religious faith or you do make aesthetic judgments about things does not mean it's unscholarly or that it's wrong to do so. It's just science does not draw conclusions about such things, right? But still, these are important topics and influence our world greatly, okay? So don't throw them on the back burner. And these are still things to think about. Okay, so science in sum, right? I've talked a lot. I'll give you a lot of information. But in summary, what I just said, though hard to define concisely, science has a handful of key features that set it apart from other areas of human knowledge. Right? The science checklist, the 7 components that we talked about earlier, matches up to a diverse set of human endeavors, from uncovering the fundamental particles of the universe, such as atoms, to studying the mating behavior of lobsters, to investigating the effects of different economic policies. Right? That checklist that we talked about is important in solving all these problems. And we've also seen that science has limits. Right? So science isn't everything, but it is important. Science helps us construct knowledge about the natural world, knowledge that can be harnessed to improve our lives and solve problems. So then, that brings us to our next point. How do we science? How do we do that? What presented a problem? How do you test it? Right? Well, let's see. The main way to perform science, in the most simplest of ways, is the scientific method. The scientific method is a method of procedure that is characterized in natural science, consisting in systematic observation, measurement, and experiment, and the formulation, testing, and modification of hypotheses. Okay, that's the definition of the scientific method. And in previous course, I believe all the way back in early elementary school, you've been introduced to the scientific method, right? And as far as we know, that's about as deep into science as we've gone. Okay. Founders of the scientific method: Galileo Galilei and Sir Francis Bacon. Credited as founders of the scientific method. Okay. So what is it? What are the steps? And by the way, for the purposes of this course, this is about we're going to follow this pretty closely, especially when we do experiments. But I want you to know that it has its limitations, and sometimes science can be more than this. Okay, we'll talk about that in a minute. But basically, the method are these steps. First, to recognize a problem. What are we trying to solve? What are we trying to discover? Next, establish a hypothesis. What do you think is going to happen when you perform an experiment or do some sort of test? What kind of results do you expect? Next, predict the consequences of the hypothesis. Okay. Perform experiments to test the predictions. Perform the experiments. Finally, formulate the simplest general rule that organizes the three ingredients: hypothesis, prediction, and experimental outcome. Okay. Often it's abbreviated as the conclusion, right? If you can see me, I'm doing air quotes. Okay. Conclusion. And that's the ultimate goal of the scientific method. But like anything, it does have its limitations. And the scientific method is not the only way to perform science. Sometimes you make discoveries that wasn't in the initial hypothesis, right? That can happen. It's one of the limitations. It's too simple. Okay? Like I've said, I think 3 times already. Science can be much more complicated than that. Simplified linear scientific method implies that scientific studies follow an unvarying linear recipe. Right? You might make a discovery through an experiment, and you're like, oh, well, let's go this route. What if this happens? What if we do this? It implies that science is done by individual scientists working through these steps in isolation. And that's not true. Collaboration is important, very important. Often you have someone working with you, or after you've completed it, before you draw a conclusion, you have peer reviews. It implies that science has little room for creativity because of its linear structure. That's one of the limitations. It's a linear step-by-step cookbook instruction. And it implies that science concludes, right? Not all, and like I said, that's why I did air quotes earlier. A conclusion. It's not always that. Sometimes you fail to validate a hypothesis, and nothing is learned from the experiment except that the hypothesis is rejected. Not unproven, but rejected. Okay. Another thing we want to talk about first, as we continue, is scientific theory versus scientific fact. This is an important topic that you have to understand before we start digging into some of the theories and laws that we're going to be dealing with in your course. Okay, so a scientific theory is a body of knowledge and well-tested hypothesis about some aspect of the natural world. Scientific theories are subject to change as new evidence is gathered. Okay, scientific laws are statements based on repeated experiments or observations that describe or predict a range of natural phenomena. It's typically based on empirical evidence. Okay? Understanding the difference between these is fundamental. This is more ambiguous, a law. Scientific theory is sometimes unambiguous. It normally holds true most of the time, and we accept it as true, but sometimes not always proven. Something that is accepted as true. That's how scientific theory is often defined. So the basic science, physics. For my physics students, you're going to be doing physics all year. We're going to dig deep into it, and we're going to have a lot of fun. Okay? Y'all are going to leave this course knowing a lot of physics. You'll see something outside and be like, "Oh, I know how that works," because I discovered it in physics. IPC, we're going to do physics too, and we're going to learn a lot. We're going to dig into it, but we're only going to do it for the first semester. Okay? And we're just going to kind of scratch the surface. It's more conceptual. But before we can do that, we have to know what it is. What is physics? What am I learning? Why am I sitting in Mr. Lawson class an hour in 1 hour every day? Right? Physics is the study of the basic principles that govern the physical world around us. Right? How does that definition compare to what you said on Friday when I asked you what physics is? Think about that. It deals with matter, energy, and the interactions in the fields of mechanics, acoustics, optics, heat, electricity, magnetism, radiation, atomic structure, and nuclear phenomena. We're going to touch on all of these things. We're going to learn all about this stuff, and it'll make complete sense when we're done. It's fundamental in the application and understanding of other sciences. Right? I like to think of physics as kind of a tiered structure, right? Because science disciplines are limited to the laws of physics, right? They cannot perform outside of physics. That's why it's called the basic science or the fundamental science, all right? Because no other science, geology, biology, chemistry, it's all bound to the laws of physics. So again, think back to the warm-up question on Friday. Did this discussion match or strengthen your definition of physics? Right? How is your understanding of physics different? Is it the same? Could be. You might have researched extensively on what physics is, and I applaud you for that. But if you didn't, if you just kind of went off, kind of what I know for physics, didn't really dig into it a whole lot, got my warm-up credit, boom, submit it, done. How does this definition vary from yours? Not to say yours is wrong. Yours could be correct. But just think back on it. Okay. Now in your courses, we're going to be doing mathematics. A lot of math. Mathematics is the language of science. Physical science can be described mathematically. Okay. Physical science is physics or chemistry. Okay. A lot of math in it. It's unambiguous, open to only one meaning. Okay. That's one thing about math. Obviously, there's different ways to do math, but when you quantify something, it's unambiguous. It's right there, plain and bold letters. Boom. The car is going 15 meters per second. Right? It's unambiguous. There's no other way to interpret that. That's what it is. When findings are expressed mathematically, they are easier to verify or disprove by experiment. Although important, is not the only way to study physics, but a way to quantify it. Okay, look, if you don't know what quantify is, look it up, highlight it, write it down. I'll be using that word a lot. Okay, quantify. Like I said earlier, be prepared to do a lot of math. It's inevitable. If you struggle in algebra, you may need to supplement math tutoring. Okay, especially in physics. IPC, not so much. Basic calculations about as far as we go. Physics, we're going to get into some algebra and even a little bit of trig. Okay, so be sure your math skills are good. Be sure you're right on it, because one of the prerequisites to this course is having a good algebra background. Is algebra. So I'm going to expect you know it. And I'm going to expect you to remember our trig discussions from geometry last year when we talked about trigonometric functions. Okay, so a few reminders as I conclude this video. do your warm up. I know it says the video at the beginning of the video. Do it. That's how I get attendance. Okay, there's no way around it. Do the thing. Do your job. I expect you to every day, without fail. Just as you get up in the morning, brush your teeth. Do your warm up. Read the syllabus and enroll and remind. If you have not read the syllabus, it should be in your class stream. Okay, go back to your class stream about a week ago, and you'll find the syllabus where I posted it. Read it, know it, learn it. I'm going to test you on it. Class policies, because in the case that you do come back to school and we do enter this classroom normally and we kick COVID in the butt and we say, okay, we're done with this. We've won. We're going to really follow those classroom rules very strictly, okay? So read the syllabus, and there's instructions on how to enroll and remind in there. There's instructions on how to access my website that has all the course resources we're going to have this year. There's a link to my YouTube channel where you'll find this video and many others. Be sure to enroll in CK12. You should have done that on Friday. Be sure you do it now and complete today's assignment. Following this video, after I post it, I'm also going to post a Google form that kind of highlights the main points of this video and this PowerPoint. I'm also going to share the PowerPoint presentation with you so you can look through it and reference it. It'll also be on my website, okay? And continue to be amazing. Don't settle for anything less. Don't be lazy. Seize each day. Start the day and try to be the best version of yourself. Log onto that computer not because you have to, but because you really and truly want to learn something new. If you change your perspective of school and learning to that, it's not something that's required of you, but something that you have the privilege to do, then you'll never have a bad day. Well, you may. Some things are outside of your control, but you'll be amazing. Okay, so that concludes this video. Be sure you do those things, the reminders. If you have questions, shoot me an email and or a private message on Google Classroom. Be sure you subscribe to my YouTube channel where you have access to these videos all the time if it's removed from Google Classroom for some reason. And y'all have a great week, and be sure to kill it in your other classes.